it's a different timing. Tell your friends to come when they are meeting. But if they have registered all the MSc students, they should come 40. Okay? Tell them all. Yeah.
Okay.
Sorry.
Where? In my pocket.
पहले उनका कराओ मैं हाँ दूसरा उनका हाँ एक्सपर्ट करा
I have to sign.
Yes.
Where?
One is here. For the one.
Then?
Sorry. Number of things you have है ना हो गया उनका हो गया ना मेरा मैं कर
The first lecture, I prefer to do it on the board. In fact, I'm more used to do lectures on the board. So I have a few remarks, questions on.
It's not on.
It's not working.
It's not on.
It's working. Hello? Yes, it should be working.
Hello, check. Hello. It's working.
Okay, thank you. Thank you. Okay, so I have a few remarks on something we said last time. So we said that we have the sphere. We have the torus, and then we have these closed surfaces. Closed means compact, without boundary, of genus 2, 3, 4, and so on. This is a closed surface of genus 0. And this is closed surface of genus 1. Then I said that we have three different geometries: spherical, Euclidean, and hyperbolic. Here, this is a subset of the sphere, the map of India. This is a subset of the sphere here. The only surface without boundary which is spherical is the sphere itself, but I have subsets of the sphere, right? And then the interesting problem is to study the distortion from spherical surfaces to the plane, and this will be the subject of my second lecture today. Okay. Now we said that. This is a Euclidean. So here the sphere is equipped with its usual metric, with its round metric. Okay. Here, when I say that this surface is Euclidean, it does not mean that it's equipped with this metric which you see here, which you visualize, which you imagine as a subset of like a donut, you know. The donut is not a Euclidean surface. So what does it mean? What does it mean that this is a Euclidean surface? Somebody can tell me what it means? We more or less talked about this yesterday. I want to be sure. That you understand? What does it mean that this is a Euclidean surface?
Quotient of the upper plane.
Yes, it is quotient. This is one property or definition. Yes.
The metric comes from.
Yes, exact. So we said that on this surface, the metric comes from. The metric comes from the Euclidean metric, where I do abstractly this identification between this side, and between this side and this side. It means that each point on this surface. So let's see a point here. There's a small disk around it, which is the Euclidean plane. Okay. So my point now is okay. I drew this. Every point here has a disk around it, which is the Euclidean plane. What happens with these points? In fact, what happened with this point? Yes. So this point, after after my identification, is identified with this point. So here I have this half disk here, and here I have this half disk here. So in the resulting surface, this point also has a disk around it, which is the Euclidean plane. Okay? Now, okay, so what happens here at the corners? What happens at the corners? Exact. So a point on the corner, which I see abstractly as a point on the resulting surface, it has a disk around it, which is the union of these four disks glued along. This is glued along this. This is glued along this. This is glued along this, and so on. So this point has a neighborhood. It has a disk around it, which is part of the Euclidean plane. Okay. This is what I mean by the fact that this is a Euclidean surface. Now, let me make a remark. My other easy remark is that we also said that when I identify the sides of a parallelogram like this, then I obtain also a Euclidean surface, which in general is not isometric to this one. There's no distance preserving map from this surface to this surface. We talked about lengths of geodesics and so on, because a distance preserving map should preserve the lengths of shortest curves and so on. So what happens here? It's the same thing, and the discussion around these four vertices here is the same as before, because here I mean the four angles add to 2 pi, right? Let me just say a remark here. What about the general case? What about more general case? You see, I take a quadrilateral like this. Okay, and then I do an identification. I take a Euclidean quadrilateral, and then I do an identification between this side and this side. I must use some homotety, right? It must have some dilatation. So I can make here the gluing. I find something which is not a Euclidean surface. You agree? Because there's no. If I take a point here, then a small a small half disk around it, a small half disk. They will not glue to give me some neighborhood of some point in the Euclidean plane. I find something interesting. In fact, this will be the domain of projective geometry. You see where you have lines, you don't have distances in projective geometry. You have only lines, and you have ratios of line and so on. So this is something else, which is very interesting, in fact, but it's not my subject. I'm just mentioning this, and I want to. Okay. Yes, I want to arrive here now to the hyperbolic case. And I want to do the same thing, the same kind of construction. First of all, there's a topological construction of a topological surface. We're talking now about closed surfaces of genus 2, which is obtained by gluing some polygons in the plane. Those of you who had some topology course on surfaces know how to do this. If you don't know, I will not spend too much time on this, but you take you take an octagon, 1, 2, 3, 4, 5, 6, 7, 8. You take an octagon in the Euclidean plane, and then you identify sides. The usual identification is like this: A, B, A inverse, B inverse, inverse meaning that the arrow is on the other side, and then C, D, C inverse, D inverse. This means that you identify this side by this side to this side following the arrows. You identify this side with this side following the arrows, and so on. You do 4 identifications. What is the result, in fact? The result is topologically, the result is a surface the result is this surface, and there's a picture. A picture which you learn if you have a course on such things. So on this surface, you see you have this curve and this curve, and then you have this curve and this curve. So these curves are let's say A, B. This is A, this is B, and this is C, and this is D. You can do this exercise when you are at home. If you never did it, you cut a paper, or you do something with. Some people do it with fabric, with pieces. You construct this. In fact, you can visualize this very easily if you do the inverse operation. You start with this picture. And then you imagine cutting the surface along these 4 closed curves. And you do it gradually. First, you cut along this, and you try to draw what is the surface you obtain. Okay, and then you cut along the second one, and then you cut along the. You see, it's when you have this torus, and you have these. This is A and this is B. Here it's easier to visualize. When you cut along B, you get this cylinder. You can open it. And when you cut along A, when you cut along this cylinder along A, you get this way, okay? Here it's the same thing, a little bit more complicated, but it's not difficult at all. Now, my question is, okay, so this Euclidean octagon, I have a Euclidean structure here at the beginning, but what happens when I do this gluing? Can I get by chance a Euclidean structure on the resulting surface? This is a natural question, right? So the answer is, well, I get a lot of points. I get a lot of points which have Euclidean disks around them. So the people who live on this surface think that they are in Euclidean geometry. Now I want to glue this side to this side, and I want the result to be a Euclidean surface. So the two sides must have the same length, right? So why don't I start with a regular octagon? You see, I want a regular octagon. The only way I can do this is to do this, and then I draw a regular octagon. In this case, there is no question about the fact that when I do the gluing here, I can glue this with this by a Euclidean isometry, and yes, and then the resulting point in the quotient has a small disk around it, which is Euclidean. So, but there's still a problem. Where is the problem? Yes, the problem is only at the vertices. So all these vertices, you see, when you do all this gluing, this is identified with this, because B with B. This is identified with this, but also this identified with whatever, with this, and so on. By this gluing, all the vertices of my polygon are identified to a single point. And this is what you see here, in fact. This is. Okay, so what is the problem with the vertices? In the previous case, which I erased, I had a point with 4 sectors, and the angle adds to pi, so it's in the Euclidean plane. Here, I need the sum of the 8 vertices to be how much? Yeah, to be 2 pi. I need the sum of the 8 vertices to be 2 pi. Is it possible? So each vertex must be pi over 4, right? Do I have a Euclidean triangle with a Euclidean octagon where the angles are pi over 4? Is this possible? No, right? This is not possible. So I try in the yes.
It's not good shaking.
Okay. Thank you. Okay. So in the hyperbolic plane, I can do maybe I can do the same construction, you know, taking lines in the hyperbolic plane, geodesics. I can get a hyperbolic surface. I can get a hyperbolic surface if each angle is equal to pi to pi over 4. The pi over 4 is, yes, okay. So last time,
Reduce.
okay, thank you. So last time we constructed a regular octagon. No, we constructed regular hexagon, so it's something else. My question now is, if I find in the hyperbolic plane a regular octagon with angles pi over 4, then I'm very happy, in fact. I found a hyperbolic metric on a surface of genus 2. Okay? So the construction is almost the same. Well, no. In fact, let me tell you how you construct this. I used a different construction, but I could have used this construction. Okay, this is my hyperbolic plane. Let me mark 4 points on the boundary, equidistant from each other. This does not mean anything in hyperbolic geometry because the distance between points on the boundary is not defined, in fact. But for my picture, it is okay. So I take this, and then I construct this. I know that I can construct. Well, I know. I see that there's a very symmetric, with respect to this representation, octagon with zero angles at infinity, right? We talked about ideal triangles, so this is an ideal triangle here, this is an ideal triangle, and so on. Now I have ideal, this is an ideal octagon. And then what do I want to do? This is my center, and then this ideal octagon, I want to make it not a non-ideal octagon, a real octagon in the hyperbolic plane by approaching all the vertices at some equal velocity. You see, I do this in the same way because my picture is symmetric. Then I can do the thing symmetrically. So these I make them come towards the center. 1, 2, 3, 4, 5, 6, 7, 8 in a symmetric way. Now I didn't draw it symmetric, but it should be symmetric. Okay. Then the angles here are no more 0. These are angles in the hyperbolic plane. And the angles, I mean, because the world is like this, the world is ordered, you know, these angles are increasing, right? Here I had 0 angle. Now here the angles when this comes towards the center, the angles will be increasing, right? These are pieces of circles until pieces of circles perpendicular to the boundary, until it becomes a very small octagon near the center. And now we said something last time. We said that, hyperbolic geometry, like any Riemannian geometry, is locally a Euclidean geometry, right? So when the octagon will arrive here near this point, the angles will be how much? 2 pi? I don't know the answer. I need someone to be sure to tell me the answer. What is the answer for octagon? We already wrote it there. Pi over 4. Huh? The limit is how much?
Limit is 3 pi over 4 maximum.
3 pi over 4.
Yes.
3 pi, thank you. 3 pi, you are right. So 3 pi over 4 is the limit, in fact. When this octagon becomes very, very small, the angles are 3 pi over 4. So the angles, of course, they increase continuously from 0 to 3 pi over 4. From 0 to 3 pi over 4. So in between, there is an, we looked for, we wanted 5 pi over 4 this. We wanted pi over 4 before. So there is I write it here. So there is a regular octagon in the hyperbolic plane whose angles are all pi over 4. Everybody agrees? And then, well, I do this construction, and this is it. I find this surface. I find a hyperbolic metric on a closed surface of genus 2. Right? And now, well, you can vary this construction. This is a little bit more complicated, but you instead, so you make, here you have, suppose this is my picture, you can change the lengths of A, change the lengths of B, you can change all these lengths, you know. The important thing, so you have polygons, where is it? You have in the hyperbolic plane, you have polygons with which you want to construct closed surfaces of genus 2. So the important thing is that so this is A, B, A inverse, B inverse. You see, I want this to be equal to this length to be equal to this length to be equal to this, and so on. In my picture, they are not equal, but this doesn't say anything because in the hyperbolic plane, this is this here is equal to this line is equal to this line, you know, because as you understand now, when you approach the boundary, visually the distances become smaller. So this is now this is a way. So we constructed one hyperbolic structure on a closed surface of genus 2, because we took a regular hexagon. But what I'm saying is that you see varying the lengths, and this becomes a complicated problem. But there's some literature on this problem, and people, even you can produce pictures on the computer. So let me put a statement here. On a surface of genus, on a closed surface of genus 2, well, there exists a hyperbolic structure. This is what we said. This is, you have understood the proof. what I want to say is that, in fact, there exists more than one hyperbolic structure. There exists a family of hyperbolic structures obtained by varying the sides of the hyperbolic octagon. In fact, it is a theorem that all hyperbolic structures on this surface, you can find them like this by doing such a. And then the thing which I want to say, a family. Yes.
When you say length, you mean
No, hyperbolic length. Yeah. All this is hyperbolic length.
so it's dependent on the angle, right?
Different from what?
But it's dependent on the angle then.
Yeah. But first, yes, you are right. Yeah, the angles must add to 4 pi. I vary the sides, but I keep the sum of the angles. Sorry. Yeah, you are right. Sorry. This is regular, but I want to keep the sum of the. I want to keep the sum of the angles. Yeah, this is. He is right in stressing on this. I vary the sides, but of course I want the sum of the angles around this resulting point on the surface to be equal to 4 right angles, right, to 2 pi. So on a closed surface of genus 2, there's this family of, and there's a dimension. So the dimension is the number of parameters. The number of parameters, I think you cannot guess them from what I mean, the number of parameters will be, so as I mentioned, I think at the beginning, and this is the dimension of the Teichmüller space of the closed surface of genus 2, right? How many parameters there you have? I don't think you can. So the dimension is the general 6g minus 6, and here g equals 2, so the dimension is 6. So the space of polygons in the hyperbolic hyperbolic plane, the space of polygons where the sum of the angles adds to 2 pi, and where this side is equal to this side to this side, and so on. I mean, according to A, B inverse, B inverse, and so on. If you count them, if you try to count them, if you have a method to count them, it must give you dimension 6. The independent parameters are 6. Okay, so this is one thing which is important. So.
Suddenly repeat that statement again. Why is it 6?
Because the general formula for let me write here, the dimension of this, well, either moduli space. You see, moduli comes from a Latin word which means you modulate means you vary. Okay, you make it smaller or bigger, you vary. And this is called the moduli space, the dimension of this moduli space, or Teichmüller space. So the Teichmüller space is a covering of the moduli space. We're not talking about this now, but they have the same dimension, covering space. The dimension of this moduli of Teichmüller space, which is the space of, roughly speaking, this is the space of different hyperbolic structures on this on a closed surface of genus greater or equal to 2 is 6g minus 6. You must count parameters. You must count parameters to find this space. I will show you how to count. There are different ways of counting parameters. so there are many approaches to this problem. This is, let me call this is moduli problem. Moduli problem.
Genus 1, it can vary.
Genus 1, the dimension is 2. It's not given by this formula. You are right, yes, it's not given by this formula. So this is kind of making this precise, in fact, which is not difficult now. We shall talk about this. Is what is called the solution to the moduli problem. And in fact, why is this a problem? Why was this a problem? What is the moduli? In fact, this goes, historically, it goes to Riemann. Riemann was very, when he writes something, he writes just small sentences, and then you must understand what he's. And in one of his papers, he wrote, well, for a surface of genus G, there are 6G minus 6 moduli. This is exactly what he wrote. There are 6G minus 6 moduli. And during at least 150 years, people tried to understand what does he mean by the moduli. Then by the work of Teichmüller, who gave an answer to this in one of his basic papers. In fact, he wrote 5 papers on the moduli problem, other problems on arithmetic. And the paper begins by, he recalls, he says that Riemann said that there are 6G minus G6 moduli, and nobody understood this, and now I will explain what does he mean by this. And then he wrote his paper, 200 pages long paper, where he explained all this theory. So this is why it's called Teichmüller space, and this is why it's called moduli problem, and because of Riemann. Okay, so this is, yes.
More question about it. If you add punctures to that,
Yes.
Can something comment about the dimension?
The dimension becomes greater.
Is there a formula?
Yeah, there's a formula, 6G minus 6 plus 3P, the number of punctures.
What is the question?
He said if you add punctures, in fact, if instead of surface of closed surfaces I allow punctures, you have to, in fact, when you say punctures, you have to make precise what do you mean by puncture from the geometric point of view, not just from the topological point of view. Okay, so from the geometric point of view, the most, the case which everybody considers and which is the most interesting is to consider surfaces with cusps. So hyperbolic surfaces with cusps. So what is a cusp? Maybe I will explain now what is a cusp. Because I want to say something about cusps. Yes. So this is and this formula works even for torus with cusps. So what does the formula give for a torus with cusps? It should give 2. Is this correct? No? 6 minus 6? No, so you're right, thank you. This is 2. This should be 2, I'm sorry. For me, 2 and 3 are the same. So this is 2. Yeah, I'm glad I corrected this. Yeah, 6G minus 6 plus 2P. I can use the other one. Yes, you are right, yes. Yeah, okay. Yeah, this one. Okay, so now so this is a way of constructing hyperbolic surfaces of genus 2. Of genus 3, of course, you must take not only octagons, but you see, you can do the same construction. you can do the same construction. 1, 2, 3, now 1, 2, 3. And then 1, 2, 3, and then 1, 2, and then 3, so on. And you get the number of parameters. You get, I mean, it's a little bit more complicated. You get polygon with many. In Thurston's notes, you have ideas about this. You know, it's. I mean, he gives all the necessary ideas. You have to read and think what he says. Yeah. Yes. Okay. So I want to talk about something. Something else about the construction of hyperbolic surfaces, which is okay. Let me. So now, so we know that in the hyperbolic plane we have ideal triangles. This formula, for what I say, will not work. So this is always for genus G greater than 2. Okay, it doesn't work. It works for genus 1 if I have. It works also, but I'm not sure for genus 0. Let me see now. So I take a hyperbolic ideal triangle, and I take, in fact, 2 hyperbolic ideal triangles, and I glue them along their edges. What do I get? I have taken 2 ideal triangles and I glued them along their boundary components. I get this surface. In fact, I don't always get this surface, and I want to explain to you why. And this is very important to understand, because it will have also this is another way to obtain hyperbolic surfaces of genus greater than 1, of closed surfaces of genus greater or equal to 2. So let us take 2, and I want to draw 2 pictures of ideal triangles. This is one here, and this is one here. So yesterday I discussed with some students here, and they know that an ideal triangle has, in fact, 3 distinguished points on the boundary. Each ideal triangle has 3 distinguished points on the boundary, defined in several ways. One way is that there's an inscribed circle. When I do something, some construction like this for one ideal triangle, then it's true for any ideal triangle, because we explained that they are all isometric. If I take an ideal triangle here, then I know that there's an isometry of the hyperbolic plane which takes this one to this one. All of them are the same. So I take the most symmetric one, which has, by dividing my circle into 3 equal parts, this one and this one and this one, then it's clear that there's a center, and then this comes here. I mean, there are many symmetric things I can do. I have these 3 points. Okay. So now I said I take 2 of these. I want to construct a surface by gluing ideal triangles. By gluing 2 ideal triangles. The best, I mean, the natural choice is that I glue this point to this point, this point to this point, and this point to this point, right? And then I find this. Here, there's no question that I find this surface here. Now I may glue this point to a point here, I can choose this point because I'm gluing infinite lines. You know, I want to glue by an isometry of the line, by a distance preserving map of the line. I want to glue two lines in dimension 1, Euclidean or hyperbolic or whatever. There's only one real line. So I want to glue this line with this side. I have all these choices. I can glue this point to this point or to this point and so on. And what I'm saying is that if I glue this point to this point here, then something happens. Something happens, and I will explain to you what. First, I want to, you see, okay. Let's come back to this surface. We had a picture of ideal triangles at the beginning of my class, and we had these pieces of horocycles. You remember? Horocycles. Now, by the naturality of the real world, these points here, these 3 points here are the same as before, the same as the points of the points where the inscribed circle touches these 3 points. So I have now instead I have these pieces of horocycles. So I recall that the horocycles in the hyperbolic plane are these circles touching this point at infinity, and there are, I mean, at each point I have a family of hypercycles, and here there is this is called a foliation. We shall talk about foliations. A foliation means just, as I said, a vector field without the direction. So I have this foliation by horocycles, which is very, very important. And I have here my 3 points. Let's say the points are P1, P2, P3. And I am gluing P1 to this point. I am gluing P1 to this point here. And there's also the foliation by horocycles. And now I use the property which I want to use is a property of distances in the hyperbolic plane. You see, you can, as I said, you can make computations in the hyperbolic plane. You use usually you use the upper half space model because there's a nice formula for the metric, which I don't want to recall, but the only thing I want to recall is that, okay, I have now, these are two lines, two hyperbolic lines in my upper half plane converging to the same point at infinity. So, for instance, this is an ideal triangle in the hyperbolic plane, right? This is an ideal triangle. This is another ideal triangle. This is another ideal triangle, and they are all isometric. We already said. So there is a formula now. So yes, okay. And when these two sides converge to a point which is in this model is the point at infinity, the horocycles are these lines. The horocycles in this model, I cannot explain this now because it will take us too much, but the horocycles in the upper half plane model are the circles which are tangent to the boundary. including the horizontal lines, which are also considered as circles tangent to the point at infinity, there. Okay. So a very small computation. In fact, maybe somebody, for those who do not know, somebody can give me the formula for the length element in the hyperbolic plane. What do I have to write here? So ds square equals dx square plus dy square divided by what? Divided by what? Y square. Okay, so it's good. So this formula means that if you want to compute the length of a curve in the hyperbolic plane, the length of a curve like you see, you have done parametrized curves, right? A curve in the plane is parameterized by two components, x and y, and depends on t. And this is for, say, for t equals for t from let's say from A to B. This is my parameterized curves. This formula means that to compute the length of this curve gamma, I just have to compute the integral from A to B of square root of dx square plus, well, dx square of t plus dy square of t divided by y of t, and then dt. This will give me the length of this curve, like you do usually in differential geometry. And so you compute, you use this formula. And what I want to say is that if I have a piece of horocycle here of length, let's say L, and here height h, then the length here will be L exponential of minus h. The thing is that these pieces of horocycles, they grow, they decrease exponentially. The lengths decrease exponentially. You remember the first construction I showed, the construction of a Lipschitz map from ideal triangle to itself. There was a picture which I showed you, which was taken from Thurston's paper. He had exactly something like that. It was a picture with he had an ideal triangle with this foliation by horocycles, and then he had he said, okay, there's a Lipschitz map from this triangle to itself, where the distance here is t, and I multiply. I send this to the horocycle with sorry, a distance. This is a distance kt, and then I think he had a formula for the contraction here, and the contraction was an exponential. So anyway, this is the formula that you need to know. Okay, so now when you have this, let's do this gluing. We said that we glue this to this. Sorry. This one, I glued this one to this one here. So now there is, and then I have a gluing on the three sides. right? I use a gluing on the three sides. So I have a curve which comes from here to here, and here it will appear on the. I will end up on the upper side since I'm gluing this triangle to this triangle, right? The curve will start here, right? Okay. And then now it depends what I want to do. Well, it depends on the gluing between this side and this side. Okay, but let's suppose that I'm gluing all the sides by some shift to the up. Then it comes here, and 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 then here, and then here, and then here, and then here. So what is this curve doing here? This curve is what is this curve doing in the resulting space? This curve it's going somewhere to infinity, right? It's going somewhere to infinity, but its length. What about its length? What about its length? Because this is the formula here. So the total length of this curve is a geometric series, right? The total length is a geometric series, but because each time I add e minus h plus the next one, which is up, I have to multiply again by e minus h, which would give e minus 2h plus e minus 3h, and so on. Okay? So the length of this curve is finite. This curve has finite length. And it's going to infinity. So is this possible here? If I imagine my resulting surface as this one, is this possible that I get a curve whose length is finite but which converges to a point at infinity? Yes, it's unlikely. Huh? Yes. This surface here, yeah, so your friend here says that the surface should not be complete. This surface, when I draw it here, it's a complete surface. A complete surface from the metric point of view. But it cannot be this one which I am finding here, because this surface here is not complete, since there are curves which are finite lengths and which go to infinity. So this is one of the pictures I showed you. So there are three shifts now. There's a shift between for the gluing of this side with this side. There's a shift for the gluing of this side with this side, and there's a shift for the gluing of this side with this side. You see, I have three isometric maps, three distance preserving maps from the real line to the real line. If if I glue this is like a zero. This is a zero. If I glue the zero with the zero, if I glue the zero with the zero, there's no problem. I get this result. This is the surface. But depending on if each one is zero or not, I get either a surface like this. So the non-completeness means that these pieces of horocycles are converging to. So it's not a surface with boundary, because the boundary will not come. I had no boundary at all. But the completion of this surface is a surface with boundary. So there are three possibilities of the gluing. This is one. This is two, and here there's this spiraling along the boundary. This spiraling of these triangles along the boundary. This is a consequence of the fact that you see here I get when it is glued to something. It is glued to. So it starts here, then it's glued to something smaller and something smaller and something smaller and then something smaller. This is the second possibility. In fact, I said 3, but there are 4 possibilities. This is the third possibility. This is the third possibility where the shifts are all of them non-zero. And well, there is this fourth possibility, the first one, I mean the most basic one, when all the 3 shifts are 0. So gluing 2 ideal triangles may give me 4 possibilities. It gives me 4 possibilities for the resulting surface. Okay? And non-complete, but I take the completion. This is not very obvious what I tell you, that when I take the completion, it gives me a surface with boundary, but I will give you a reference to this. The completion will be a surface with 1, 2, or 3 boundary components. And the length of the boundary components, there's a formula which gives you the length, the hyperbolic length of these boundary components in terms of the shifts, in terms of the 3 shifts. This is somewhere in Thurston's notes. It takes maybe 1 page of explanation, in his notes, 1 page of explanation and so on. And then it was long ago, maybe, I think around 2010, not very long ago. I wrote a paper, a long paper, with one of my students where we explain in every detail this construction. It has to be, if you want, you can read this paper. You can refer to this paper. This is me and my student. Guillaume Terré. I don't remember the title of the paper, but it has in the title there's something with shift coordinates. These coordinates here, these are, when you glue two ideal triangles, and as I said, you have natural 0 and then natural identification with the real number. Shift means just the translation, so are called shift coordinates. Shift coordinates with something else. Shift coordinates, or maybe there's something else with shift coordinates, but the title contains this shift. So okay, so now we are happy because we have constructed one hyperbolic metric on a closed surface of genus 2. Now we are even more happy because we have constructed hyperbolic structures on this kind of surface. This is called pair of pants. So to see that it's a pair of pants, you must return it. Yes, you must revert it. Pair of pants with geodesic boundary. With geodesic boundary. Let me write some more properties that we know. As I told you, so pair of pants of different kinds. This is by abuse of notation, by abuse of name. This is also called a pair of pants with where the length is supposed to be, the length of this boundary component is 0, right? Here the length is some definite positive number, and here the length is 0. So we have constructed just by using gluings of ideal polygons, of ideal triangles, we have constructed what? Let me say, generalized meaning that some of the boundary components may be 0, generalized pairs of spans of any length of boundary components, including 0, between 0 and infinity. So this is L1, L2, L3. I have 3 boundary components. They may be between 0 and infinity. And now something more.
So
Yes.
I am not able to visualize the boundary. Could you repeat that?
Okay. Well, I will repeat what I said, but then maybe I will say something more. Okay. First, what I said is that. Okay, this is my. When I said that suppose I identify this side with this side and this side with this side with the same shift. So first thing is that this curve will end up here, and then it will end up a little bit up, and then it will end up a little bit up, and so on. And this curve has finite length and is converging to somewhere not in the surface. So right. Now, what you didn't understand is why do I get a surface with boundary, right? So for this, there's a picture, in fact, in that paper I told you about, which we did the exact computations. You see, so we are gluing this, like we are constructing the covering, the universal covering of this surface. Okay, when you glue this triangle with this triangle, and then you come back, you obtain this surface. You obtain some surface, maybe finite or infinite here, with which is not simply connected because it has this loop, right? But now I am developing everything on the universal cover. So I'm gluing different triangles, different ideal triangles. So I start with this one. Okay, I glue this. So I will do it more. I will do it on the other side, but it's clearer, in fact. Then here, you see, I am in the universal cover. This is glued to another triangle, right? In the universal cover, I mean, I have only ideal triangles glued to one. So this second triangle on this horocycle here is shorter, right? It's shorter by a definite constant, by an exponential. And then this one also is shorter here, and then I get a family of ideal triangles, and I see them. They converge to a line. They converge to and this line is the boundary component. This line is the yes. So in French, the relevé. It's the what you get up. when you have a curve on a surface, then this is called the lift. So the lift of the limit here, the limit geodesic is the lift of the boundary component. Okay, so what I was saying, we know how to. Yeah, I started there. I think we have constructed generalized pairs of pants. Now, you see, I know how to construct a pair of pants with, let's call ABC, with arbitrary lengths of boundary components. I mean, if you see this, if the shift is very small, then obviously the resulting there's a formula, in fact, which we have in that paper, of the length of each boundary component, which could be 0 or could be any real number, in terms of these shifts. This is the title of the paper: Shift Coordinates, Ideal Triangles, and things like that. Yes. What did you find? What is the title? Yeah, he lost the connection. Okay, never mind. Okay, so shift coordinates, and what?
Stretch lines.
Straight lines?
Stretch.
Straight lines?
Stretch.
Stretch lines is what I showed you, the big stretch lines. And okay, yeah, it's, yeah. Okay, so there's maybe another paper with shift coordinates, because here there's no polyhedral structure. This other, maybe, I don't know. Okay, there are one or the other. So anyway, what I'm saying is that ABC there's a formula for ABC in terms of these shift coordinates. Now, well, I take 2 of these with the same number, same boundary lengths, ABC, and I glue them. What do I get?
You're going to glue all 3 together.
No, I take 2 of these. I glue them one by one, so ABC, C prime, B prime, A prime. If they have the same lengths, A and A prime, B prime, and C prime, I can glue them. I get, as we did before for the Euclidean case, I get a closed surface of genus 2, right? So now I have another method than the polygons. This is a different method for getting this surface of genus 2, in fact. So let's say these are the two pairs of pants. One is above, one is below, and then I can continue. For surfaces of genus 3. So this is one here. This is one pair of pants. This is one pair of pants. This is one pair of pants, and this is one pair of pants. In fact, I have to have, in order to perform this gluing, the lengths have to be the same. The lengths have to be the same. But I have a choice for the twist, right? I have a choice for the twist. So my last question before we stop for now, I gave this formula here, 6g minus 6. Let's forget about the p. The p, in fact, you can do it also with this. 6g minus 6. This formula you can see it from here. So how many? So here g equals 3. How many curves do I have? 1, 2, 3, 4, 5, 6. I have 6 curves. And as we said, for the curves, we can choose the length of the curve as we want, right? And then there is this twist parameter. So I have here I have how many parameters? I have 6 plus 6. This makes 12 parameters for this surface here, and the genus is equal to 3. I hope it works. So 6g minus 6 for g equals 3 gives 12. Okay, so I was correct.
What are the six parameters?
Huh?
What are the six parameters?
The 6, first there are the lengths. The lengths must be the same, and I have 6 lengths, right? And then when I have this, when I want to glue this to another pair of pants with the same parameter here, I have also the choice of turning, you know, the twist. I have the choice of the twist. For each curve, I have 2 parameters, the length and the twist, and it gives me surfaces which are not isometric. I mean, you have to prove this, but the surfaces are not isometric.
For each joining, you have 2.
For each joining, I have 2, the length and the twist. So this is, and these are called Fenchel and Nielsen parameters. Fenchel and Nielsen parameters are these twist, are these length and twist parameters associated to the, yes. Yes, you have to prove that you get different surfaces, but you get different surfaces when you glue. They are not isometric. For instance, if you want an idea for this, why you get so you see, if you agree on the fact that which I mentioned before, but I will talk about it later, that the isometry type of a surface is determined by the collection of lengths of its simple closed curves. The lengths of the closed curves determine the isometry type of the surface. So now, okay, I have a surface here. Well, when I say the length of curves, I mean the length of the closed geodesics. Like yesterday we discussed this closed geodesics of the torus, so whether the shortest one must agree, then the next one must agree, and so on. So here, okay, this is a closed geodesic. When I glue according to the fact that the length agrees, I glue. But then now, if I make a little turn, you see, I have this other closed geodesic in the resulting surface. I have this other geodesic, closed geodesic. When I change the gluing, then yes, the length must change. The length will change, and this is something you prove. This is something you prove, that the length of this new geodesic cutting it. Well, it can become less. It can become. This length function is convex. This is a general result. The length function is a convex function, and so there could be okay, it's convex. It's like this. So there could be 2 points where the length is the same, but then you take a third curve, and the third curve, the length of the third curve will necessarily be different. When the length of this curve is, then you take, for instance, this one, and then you. This is the part of the technical part of the theory. The length and the twist parameters determine the hyperbolic surface. Okay, so I think it's time to for the cakes. In fact. Yes, tell me. Yes, you have questions?
Anyone has questions?
Yes?
So when you say lift, it's the covering?
Yes, the covering. Yeah, to the universal covering.
Yesterday we were doing lifting of maps and paths, so that's what it is about.
Yes, to the covering, yes.
So, genus 4
Yes.
One you can keep it in a row.
Why I can keep what?
The holes first.
Yes,
One,
yes.
2, 3, 4.
Yes.
You can also make it 1, 2, 3, 4.
Ah, the points.
The holes.
The holes,
genus.
yes, okay, the genus, yes.
And it, I don't see how they still have the same parameters.
Okay, I mean, I think that you are 1, 2, 3, 4. This is genus 4. I don't know why you want it to be like this, but it doesn't matter. It's the same. Yes. So this is the complicated thing for you?
It's the same thing.
Yeah, it's the same thing. Yes. I mean, topologically, it's the same surface. You see, I just move this here, I move it here, I get this.
No, in terms of metric.
In terms of metric, this has nothing. I mean, you see.
These pictures are not.
Yeah, these pictures are not realistic at all. This is the point. In fact, in hyperbolic geometry, I mean, you just can represent a surface, for instance, like this, just to stress on the fact that there is a very, very short geodesic. Okay. You can make also this geodesic very. In fact, it's a question of. It's a question of it's a question of the geometry of the pairs of pans. You see, you start with the pairs of pans. You have a the pairs of pans which I drew, like this one or like this one, they are all unions of two ideal triangles. And we said that the area of an ideal triangle is some fixed number. I don't know, pi, okay, pi. So since any closed surface, or since this pair of pans is a union of two ideal triangles, its area is necessarily 2 pi. So when I make these very small, then there should be lines which are large, in fact, because the area, it cannot be, I cannot draw it like this. This is not a pair of pans, because the area must be 2 pi. And conversely, if I make, if I have very, very big, boundary lengths, then there should be a very, very small piece of fabric joining them. So you can, I mean, when you tell me, okay, like this, I have a perfect surface. So this is also a hyperbolic surface, but it just it doesn't show the reality. This is upside down. In fact, again, this is usually drawn like this. No, up. And this is a kind of pair of pants which Sullivan calls a bikini. Because if you enlarge the boundary components, then there must be too small fabric.
Any other questions, comments? Okay, so let us thank Professor.
So except sphere, no other genus surface.
The sphere?
Except sphere, no other constant curvature surface can be seen in R3, right?
I think so. Yes, you're right. Yeah, this is correct.
Pictures
Well, except maybe the surfaces it will not be compact. It will not be complete. No, because there are these pictures of embeddings of the hyperbolic plane in R3.
Euclidean surface, yeah, like OS. Flat
Euclidean,
torus can you not be?
no, cannot be, no. But for the hyperbolic, on Teichmüller space, the basis was this construction of best maps best Lipschitz maps between hyperbolic surfaces So this was the main tool for this metric. Now I want to talk about something which I mentioned. This is the the Teichmüller metric, which is older, much older. This is Thurston's paper, 1985. This is Teichmüller. His work is in beginning 1940s, or maybe 1937, something like that. And I want to, of course, you have other metrics. In fact, a Teichmüller space is a space where you have other several metrics. There's a metric called the Weil-Peterson metric, which is also a famous metric. So Weil is André Weil, who spent 2 years in India, in Aligarh. Aligarh, yes. Okay, thank you. I don't need this now. I don't need this now. I need this thing. It's correct, but I don't need it now. Now I will, yes. Yes. Thank you. Yes, I will use later. Yes. So this.
So this is the pointer.
Yeah, I want to cancel this.
Okay, you want to shut it down, sir?
No. Well, okay. Well, let's keep it. But this has nothing to do with what I'm telling you today. Okay. So let me tell you what is this Teichmüller metric about. I want to start with the something called the Riemann mapping theorem. So the Riemann mapping theorem tells you the following, that if you have, say, any simply connected subset of the disk, which is not the whole complex plane. If you have a simply connected subset of the complex plane, which is not the whole complex plane, then you can send it by, and this is the round disk. Let's say this is the disk, disk of radius 1 by a holomorphic or angle preserving map. Which is a difficult theorem, in fact. It's not at all obvious that you can send any simply connected subset of the plane to the round disk. So Riemann had a proof using physics, which was considered as not very rigorous for many years, but nobody had another proof. And then other simple proofs came, and now you can find proofs in Alfor's book or whatever, any book on complex analysis. This is, I think Thurston also has a proof. Okay, so now naturally you ask other questions. Okay, let us take a subset of the plane which is not simply connected. For instance, this kind of set. An annulus. Can I send it by a angle preserving map to a round annulus like this?
Maybe you can send the inside part to that.
Yes, the boundary. Sorry, yes, you're right. Yes, I mean this part to this part. Yes.
Yes. Can you do that? The inside part is sent to that. The inside part
Yeah, in fact, I can send all this to all this by an angle preserving map, but it will not send the inside part to the inside part. If this is your question? No. No.
So that's the blank part, right?
Yeah, this is the empty part, and this is the empty part.
So empty part.
This is a topological annulus. This is also a topological annulus. The answer is yes, in fact, provided what I drew here is a Euclidean annulus. You see, this is a circle, and this is a circle, and this is a radius R1, and this is the big one, and the small one is radius R2. Yes, the answer is yes, but you have to choose. You have yes for a particular so the ratio of R1 to R2 must be chosen conveniently. No, not for every. And this ratio is called, well, this is the ratio is called conformal invariant. This is a conformal invariant for such. So any well, instead of simply connected, this is one connected domain. One connected domain has a well-defined conformal invariant which is this ratio when you send this to a standard annulus like this. And then the theory is more, much more general, in fact, this theory of conformal invariance. You see, you have you may ask naturally the same question for this kind of, so this is in the complement, this is in the complement, and so on, and so on. And there's all this theory of conformal invariance, and then you have, you may remove infinitely many disks and say, so the first theorem tells you that up to a conformal, conformal means angle preserving. Okay, so the first example, the first statement I made there tells you that up to a conformal invariant, there's only one subset of the complex plane. All the others are conformally equivalent to this one. For doubly connected domains, you have essentially one, but with parameters, the ratio, these two ratios, and so on. There's all this theory, which is a very interesting theory.
But
now,
if you change that surface, then your anglers will also change, right?
If I change this,
Slightly.
but it depends. Yeah, it could be. You may change it, and then it's the same. I don't know. This is a complicated thing. It could be different. It could be different, but not necessarily. Yes. So okay. So we have these conformal invariants of subsets of the complex plane. Now we take the problem from another side, and we say okay, this is a simply connected. This is triply connected. So I remove this. I remove this. I remove these two. And then let's make it only with two. This is a doubly connected subset of the plane. This is doubly connected. And the ratio is not the same, different ratio. So I know there is no conformal map. And you say, okay, what is the best close to conformal map? Is there a best close to conformal map between these two surfaces? And if yes, then you will have a distance between the two surfaces. So I will explain what I mean by all this. The thing I want to say to relate to the previous talks and so on, we will put a new distance between surfaces using the fact that what is the best close to conformal map that sends one to the other. Okay? So what is this theory of close to conformal map? So there are, in fact, there is this theory of quasi-conformal map. Quasi-conformal maps. Quasi-conformal maps. They give rise to quasi-conformal constant, a number. And the question now about distances is, I want to measure the distance between this surface and this surface as the logarithm. The logarithm. You remember we took logarithm for the first distance. The logarithm of the best quasi-conformal distance between them. And you get a metric on surfaces. You get a metric on spaces of tori. You get a metric on spaces of surfaces of genus G, and so on. And this is called the Teichmüller distance. This was developed during during several decades after Teichmüller wrote his paper, because his paper was very different, very difficult to read. It was developed by analysts because it involves a lot of analysis. You know, when you do complex analysis, it's also analysis. It was developed by algebraic geometers. So I was just talking with one of your professors. There are a lot of papers on algebraic geometry on this Teichmüller theory. And then it was developed also by Thurston, who made it much more geometric, in fact. I understand Thurston's papers, but I'm not at all... I mean, when I start reading an analysis paper, I'm lost with the formulas and I'm not interested anymore. Same thing for algebraic geometry. But I want to explain to you the way I see it, which is close to what we said before on Thurston's metric. So let me start from the beginning, and let me tell you what is a quasi-conformal map. So okay, so what is a conformal map? A conformal map between surfaces. I said this is an angle-preserving map. So you can understand this in many examples. So I say I have a surface. I have a surface. I have an angle, say between two lines. I look at the image of this point, the image of the angle, and the angles must always be preserved. This is not a very this definition is not very useful, in fact, because how would you do, in fact, to measure the angles and say that all the angles are preserved and so on? So there's this. Yeah, this is also a very good question. Yeah, what is an angle, in fact, if I'm not... So these are... I'm considering subsets of the plane, and I took straight lines, so the angle, we know what it is, but if it's a general Riemann surface, and what is the meaning of an angle, as he said, and so on. This is why I will... So this is the idea. They're angle preserving, but I want to do it otherwise. I want to give the more precise definition, in fact, which is usually the one which is useful. Okay, so I have... I didn't tell you, but we started with... for the Riemann mapping theorem, we started with some simply connected domain from the plane, and I said that this simply connected domain is sent to the unit disk by a conformal. I can find a conformal map or an angle-preserving map, or angle-preserving map that sends this to the unit disk. This is called the Riemann mapping theorem. Now, there are generalizations. There are many generalizations, and the most general statement is called the uniformization theorem. And this is attributed to Poincaré and Koebe. I think the year is 1916 or something like that. I may be wrong because I don't remember dates usually, but it should be some. No, it's not 1916 because it was much before the war, maybe 1907 anyway. Poincaré and Courbet. This is Riemann mapping theorem. This is Riemann. Riemann is for subsets of the plane, and the Poincaré-Courbet theorem is for any surface, in fact. And usually it is formulated in a geometric way, saying that any surface that the complex structure of this Riemann surface is the one underlying a metric of constant curvature. And what do I mean by a metric of constant curvature? Now you know. Either a Euclidean metric or a spherical or hyperbolic. Spherical, Euclidean, or hyperbolic. This is the most general form of generalization of Riemann mapping theorem. This is the universalization. So when I told you that all these surfaces admit a metric of constant curvature, positive, 0, or negative, this theorem is saying much more, in fact. It's not only saying this. It's saying that if I have this surface here with some complex structure on it, so this precise complex structure is underlying, is associated to a Riemannian metric of constant curvature. Like there in the Riemann mapping theorem, I'm not just saying that a subset of the plane has a Euclidean structure. I'm saying that, well, this subset of the plane carries a complex structure which is carries a Riemannian metric of constant curvature, which is yeah, I guess this is a very for subsets of the plane. This becomes but for a subset of free space like this, subset of free space like a cap, it carries a Riemannian flat structure, which is compatible with its angle structure. This is the meaning of a complex structure for surfaces. Is any complex structure of any complex structure of the surface is the one underlying some metric of constant curvature. This is why it reduces the study of all these complex structures to a special class of complex structures which have a constant curvature. Okay, so I'm going fast here, and it's the end of the day. And let me just mention also that this since we mentioned Thurston for several times, this uniformization theorem has an analog in three dimensions, which is the famous uniformization conjecture, which was conjectured by Thurston in the 1970s, and which was proved by Perelman in the 2003, 2004. It was a generalization of this uniformization theorem for three manifolds. In the case of surfaces, there are only three possibilities: either spherical, hyperbolic, or Euclidean. In dimension 3, there are several possibilities, but not many, in fact. 8 only. 8 kind of geometries. One of them is the three-dimensional spherical geometry. One is the three-dimensional hyperbolic geometry, and one is this three-dimensional Euclidean geometry, and there are 4 others. Okay, so this is a very long introduction. I want to go forward. So now, in this theory of the surfaces, so the first thing I want to explain is we want a measure for non-conformality. Conformal means angle preserving. We want a measure for the non-conformality of the map. So this is done in the following way. In the easiest case is, suppose the map is differentiable, C1. So this is a map F from one surface S1 to one surface S2. The map may be conformal, maybe not conformal. Conformal means angle preserving, but we want something to be here. Your friend asked me, so what does it mean, angle preserving, for subsets which are not subsets of the plane, and so on and so on. So the good definition is for maps which are C1. When I said that analysis people worked on this, so the analysis people do not consider only C1 maps. They consider maps which are much more weaker than C1, and this is the theory which I don't want to enter into. But suppose the map of C1, the map is differentiable. So you have done a little bit of differentiable maps on surfaces, differentiable maps between surfaces. You know that there's a derivative. There's a derivative of a differentiable map. The derivative goes from the tangent space to the tangent space of the target, and if the map, well, the derivative, let's call it df, which is a linear map. If the map is conformal, somebody can tell me something about this derivative? property of this derivative of a conformal map if the map, yes?
It is a similarity transfer.
Yes, yes, right. He said that similarity is correct, and you?
Yeah, DF is not German. DF should be an invertible transform.
No, the invertible is, it should be invertible, I mean, it has nothing to do with the fact that it's angle preserving or conformal. So the derivative is of a conformal map, as our friend there says. I want to say it differently. It sends, well, and you can take it as a definition now. You see, when somebody asked me, what do you mean when you say infinitesimal? What does it mean? You asked me, right? So infinitesimal means instead of looking at the manifold, you look at the tangent space. Okay? So on the tangent space, the map, the infinitesimal form of the map is just the derivative which acts on the tangent space. So it sends an infinitesimal circle to an infinitesimal circle. To an infinitesimal circle. This is what, even if you don't know what's conformal map, what is then you must. So you see, let me say it differently. Let me say it differently. So I have a surface. I have a surface in free space. A metric, a surface equipped with a metric. Let's think that our surface is equipped with a metric. So I have a point here, and I have an image of this surface here. This is the image. I can draw. You see, I can draw a geometric circle around this point in the surface. That is some points at the same distance, situated at the same distance from this center. This is a geometric circle on the surface. It could be wiggled like this because the surface can be. I mean, there can be yes, up and down and three dimensions. So anyway, you draw a circle, and because it's a homeomorphism, its image is also a circle. It's also a circle for this new in this new metric, and the circle you can make it smaller and smaller. This is the meaning of infinitesimal circle. This circle, I make it smaller and smaller. To do it precisely, you must talk about tangent, about the action of the map on the tangent space. This is why I suppose it is differentiable. So anyway, you have here either you can do it on the surface or on the tangent space. If your map is angle preserving. This is a property of angle preserving maps, is that either, let's do it on the tangent space, it takes a circle in the tangent space at this point to a circle. This is what our friend meant when he says it's a similarity.
The radius will change.
Pardon?
The radius will change.
Yeah, the radius will change. The radius will change. The radius will change. The radius will change. Now, if the map is not conformal, what can be the image of a circle centered at the origin? This is also differential geometry. The image is an ellipse. Because you have a derivative, and the derivative there's some direction which is moved contracted, and the other one you have to deal with the linear map with yeah, right. So you have eigenvalues and so on. The image in the general case of a C1 map, the image here in the tangent space is an ellipse. Okay, and now we are happy because the degree of non-conformality or of non-angle preservation at this point P, this is f of P, by the ratio you see this is an ellipse now in the new tangent space, in the tangent space of the image. This is an ellipse, and the ellipse has a small axis and a big axis, right? This ratio let's call it B, this big axis, and this is a small axis, B over S. Ratio of this big axis over the small axis. At each point. And then I'm simplifying a little bit, and then the supremum of this B over S over all the surface well, is a measure of the non-conformality Okay, so now we have a measure for each map of how much is it far from being conformal. In fact, I take the log instead of the supremum, so that when the map is conformal, then this measure is 0. Whereas here, if I don't take the log, when the map is conformal, then the supremum will be 1. But we want a metric, so we want the distance to be 0. When there is an angle-preserving map between the two surfaces. And now, so I would say this in other words. Let's call this K of F. F is the map, and I'm measuring the degree of non-conformality of F. And now I have two surfaces. S1 and S2. I want to define the distance between S1 and S2 as what do I want to do? How do I want to do it now? Because I told you how we define the first distance. So this is we take some infimum over all maps F, which are, say, differentiable between S1 and S2. We take the infimum of what? Of, I call it K of F. You are right. In fact, I mean, I take the supremum over all the surface, all the points, or you are right. All the points over, because at each point I have such a quantity which is defined on the unit circle in the tangent space of this point. Yes. So I take over all the points on the surface. I look at the derivative at that point. I look at the derivative at that point, and I take the supremum of. I take B over S, and then the supremum over all points. Exact. Yes, this is the property of C1 maps. Yes. It's a similarity on the tangent space. So it's not very difficult to see that this distance d of S1, S2 satisfies all the properties of a distance. Distance from S1 to S2 is equal to the distance between S2 to S1, and then the triangle inequality, because we put the log, then the composition will be transformed into an. I mean the multiplication which comes from the composition will be transformed into an addition, and so on. And it is a property of maps between surfaces that the converse will be will have the same dilatation. Yes, tell me.
Do you need to put a mod there?
You need what?
Mod.
What do you mean by mod? No, because the soup is positive, since this is the big over the small one.
So how does d of S1 S2 is equal to d of S2 S1?
Yes, this is a property. Yeah, this is because the inverse of the inverse linear map sends the circles of the second one to the ellipses of the first one with the same ratio of big axis over small axis. Yes.
That needs proof, right?
Yeah, it needs a small proof, but it's not. This is not a difficult part. Okay, so and this is the Teichmüller distance. This gives the Teichmüller distance between two surfaces. So it gives a metric on Teichmüller space. It gives a metric on Teichmüller space. No, sorry. It's the map the surfaces are all homeomorphic. Yes. The map F which I took is a homeomorphism. In fact, diffeomorphism. Yes, it has a derivative. Yes. C1 map. Yes. C1 diffeomorphism. Yes. You don't need to know more, in fact, if you want to work on this geometric theory. I mean, but people working in analysis, they put very less hypothesis and so on, but we are happy with this. Okay, so I want to tell you several things now about this. You see, I said we have the Teichmüller distance. We have the Thurston distance. And we have the Weil-Petersen distance. There are many others, in fact. These are the three main. Weil-Petersen. Yeah, Weil-Petersen. Yeah, this is André Weil, your friend, the friend of India. And there are some others also. In fact, there's a Macmillan distance, there's a Yao distance, but these are the main three distances. And a natural question, this is just one remark I want to make. A natural question is whether for any 2 points you have, whether you have constant K1, K2, K3, and K4, such that you have this K1, K2, and then you come back to K4, Weil-Petersen, comparison between the four distances. In fact, this is not easy at all. Okay, I have, very recently we have a paper which we just put on the internet with four co-authors. Yi Wang, Kenichi Oshika, and I always forget this. Yes, whipping pan. Where we have produced these, we show that this for this. It's not. I mean, it's complicated, you know, because for instance, this distance is a symmetric distance from. All the distances are symmetric except the Thurston distance. The Thurston distance, the distance from x1 to x2, is in general not equal to the distance from x2 to x1, as I will show in the next lectures. The others are, and so you have to be careful about several things. So you can compare the four distances. The Teichmüller.
They come from Riemannian matrix.
No. This one is Riemannian. The Weil-Petersen is Riemannian. Thurston is not Riemannian. Teichmüller is not Riemannian. Yes.
Teichmüller in the elliptical case is Riemannian.
In the case of the torus, it is Riemannian. Yes, only in this case. In the other cases, it's a Finsler metric, and all the other. I mean, the Thurston and the Teichmüller are non-Riemannian. So okay. So I want to show you. I want to tell you a few things now about this. This question first, I want to show some pictures because this was supposed to be my general talk, in fact, my cultural talk, right? So this is part of what I will tell you now. Okay, so in fact, this is not the one I sent you today. This is the one of yesterday. Because I have to show you some pictures.
Yeah, right.
This is your computer?
No.
Okay.
Can you call Saurabh? Yeah, I will open my email address.
So the Weil-Petersen is Riemannian.
Only Weil-Petersen is Riemannian, yes. In fact, it is more than Riemannian. It is. It has also a. Huh? No. None of them is of constant curvature. It is a Kähler metric. In fact, it has a complex part. Yes.
Can we look up some other surface as close as we wish in terms of time?
Yeah, this is right. Yeah, this is a very interesting question. Yes, if you start with your favorite surface, what are the surfaces which are, say, a distance one Teichmüller distance from? Can you make it more precise, your question?
For instance, if I give you a constant gamma, and if I give you a surface S, can you give me another surface T which is within gamma distance from S?
Yes.
For an unfairly small gamma?
Yes. So you see there's a very, I mean, there's a well-developed theory of you have surfaces with foliations, and then you take your these are called measured foliations. I mean, it's something like you have distances also. You keep one of the foliations the same, and then you deletate the second one. You obtain surfaces, and you can compute the distance from the first one to the new one. Yes. So yes. So the main ingredient to compute distances is this one here. You have this grid, which is transformed to a grid like this. And if you manage to do this on the Riemann surface, then you have precise estimates of Teichmüller distances. Yes, thank you. Thank you very much. Okay, thank you.
So pointer is
Yes, okay, thank you. Okay, so these are the points I want to, these are the things which I want to show. You see, I was reading Teichmüller's paper because I always want to look at the originals, because usually what you find, on the internet, people misquote a paper, and then everybody misquotes because they saw that it's written in this reference, and so on, and repeats itself, and you have really a mess in all kinds of papers, all kinds of questions, because I mean, history is really complicated because of the internet and because the wrong information propagates, even in Wikipedia page and so on. I'm saying this because in Teichmüller's long paper, where he talks about quasi-conformal maps and where he defines this distance, he says the first appearance of quasi-conformal maps is from the 19th century in the work of Tissot. So I looked a little bit who is Tissot and so on. I saw that Tissot is a French mathematician who was teaching at École Polytechnique. He was the teacher of Poincaré, and he was interested in geography, in fact. And he published geographical maps, in fact, where there are. In the geography, there are in the picture there are ellipses, circles, and ellipses, and these ellipses represent exactly the quasi-conformal dilatation of the map. So this picture here is of a geographical map called azimuthal equidistant. I was planning to talk about this. Today to explain what it is, but maybe I will do it tomorrow because I'm very tired today. So azimuthal equidistant map, this is the map which was studied by John Milner in one of his papers, which I will talk about. But it's the map also, I think, this one, which is on the flag of the United Nations. Do you believe this? Is this familiar to you? No, I don't really like the map of the United Nations, but I know that this azimuthal equidistant map they use it on the flag. So what is this? So this is a map of the whole world, in fact, right? This is a map of the whole world. You have the 5 continents. This is Australia here, I think. Where is India? India is here, I think, right? India is here. But as we said before, when you build a geographical map, you cannot preserve distances. This is sure. There are maps which preserve angles. I will show you a map which preserves angles. You want map which distort angles so that distances are more or less better preserved. So this map, the ellipses here, the ellipses here are exactly these ellipses which I talked about. And they show you how the map is far from being angle preserving. Because we said that angle preserving means that it sends a circle to a circle. If it's not angle preserving, it sends a circle to an ellipse, which is not a circle. So this Tissot, he invented this way of putting of drawing ellipses on the map, so that when one looks at the map, knows that okay, this map is not does not preserve angles. Here it distorts angles very much. Here it preserves angles more or less. And so on. So this they put so the United Nations, they put the center of the world at the North Pole, which is very good. In fact, they didn't put it nor in Great Britain nor in the United States. So the center is the center.
Something to do with that this is a sphere and you're looking on the.
Yes, it's a sort of. In mathematics, it's called. Tell me something. No. Stereographic projection is preserves angles. This is called in Riemannian geometry. This is called. Tell me, please. No. It's something not geographical. It's something we use in mathematics. When you have a Riemannian manifold, so a surface, and then you take a map from the tangent plane to the surface where each no differential. Exponential map. This is the inverse of the exponential map. You can see that I'm very tired today. Okay, this is azimuthal equidistant projection. I will say more about it next time. Exponential. No. Exponential map preserves the distances from the center, and it sends every point on every ray to the same point on the same every ray on the surface to the same point. No. It has nothing to do with the exponential. No, it's called exponential, but it's not the complex analysis exponential map. So this is now, this is another map. This is another map called cylindrical. So this is a cylindrical. This belongs to the family of cylindrical maps. You see, cylindrical maps in principle are not very difficult to. I mean, they are not. They may be useful, but you have a sphere which is the globe, the Earth, and you imagine it contained in some cylinder which contains it, tangent to it along a circle which is maybe the probably it's the equator, if we can think of this line as the equator. And then you project either you project from the center on this cylinder, or you can project horizontally. I'm not sure which one. I think this one is you project from the center. And the good thing with this projection on the cylinder is that when you unroll the cylinder, it becomes really a map on the. So it's an easy way of obtaining maps. So this is a known cylindrical projection. So again, it gives you the how much it is not conformal. So the distance from the quasi-conformality. The quasi-conformality distortion of this map. The third one, I think, is the stereographic projection. This is stereographic projection. So you have a center. In fact, there are two types of stereographic projections. You take a point, say the North Pole. Yes, no, this is not the North Pole. Okay, it's somewhere else here in the sea here, not too far from India. Okay, it's on the equator, and then you you take the line. Okay, now you have to project on a plane. So the plane may be usually it's a tangent on the opposite side to the point, or sometimes on the equator. But the important thing is that this stereographic projection, it preserves angles. It's angle preserving. It's angle preserving. Do I have a fourth one? No, I don't have. I have the result of Milnor, which I will tell you about next time. Okay, so.
Any questions, comments? I think YouTube has this.
Okay, I brought my glasses this time.
I can read. How are these ideal triangles you glue together to make pair of pants embedded in the octagon you use to construct?
No, a pair of pants, and then you glue together to obtain pair of pants.
Embedded in the octagon you use to construct the two torus.
It has nothing to do, in fact. It's not related. The two constructions are not related.
So the second one is, can you say something more about Frenchel, Nielsen?
Yes, I want to say this.
And some good reference.
Yeah, next time I will talk about this.
Okay.
Yes, okay.
The third one is, are the conformal maps F defined between S1 and S2 rotational invariant? S1 and S2 conformal maps.
So this is about this, about today, about this afternoon. So conformal maps between S1 and S2, rotational invariant. No, because S1, no, S1 and S2 can be, there's no, this is S1 and this is S2. This is S2, there's no possible rotation, no.
So that's about it.
Okay, thank you.
Do you people have any questions? Okay. So let's thank Professor
Thank you.
and we meet at 2 p.m.
At 2 tomorrow, okay.
Yes.
Yes, thank you.
Just go over.
Yes?
Are there any interesting conformal invariants for specific classes of spaces?
What are there any?
Any interesting conformal invariants?
Interesting quasi-conformal invariants or special classes of spaces.
Special classes of spaces.
Quasi-conformal invariants, you mean?
Yeah.
Quasi-conformal invariants or conformal invariants? Okay, what does this mean, quasi-conformal? Because here everything is quasi-conformal to everything. There's no question of quasi-conformal invariant. I think he meant conformal invariants. There's no invariant for quasi-conformal. All of them are quasi-conformal to each other. The rest of the question is what? After quasi-conformal?
Quasi-conformal invariants over special classes of spaces.
I don't understand the question.
Maybe
No.
you can rephrase next time.
Yes, tell him to rephrase next time, yes.
This is on YouTube.
Okay, thank you.
Thank you very much. See you tomorrow. Tomorrow, yeah. 2 to 4, and then 4:30 to 5:30 we have a talk by Professor Bankeshwar Tiwari from Banaras Hindu University. So 2 to 4 is Professor Kapil. Yeah, it is online. It will be projected here and it will be on YouTube. He could not come because of marking.
So do people study topological properties of this Teichmüller space, like whether it is connected?
Yeah, it is. It's a good question, but it's.